Hi everyone. In this lecture, we'll see few problems on elementary flow, lifting and non-lifting flow, etc. And we'll see the remaining theory topics. Okay. We'll start with the problem number one. Okay. A circular cylinder is placed in a uniform stream of ideal fluid with its axis normal to the flow. Relative to the forward stagnation point, the angular position along the circumference where speed along the surface of the cylinder is equal to the free stream speed r. Options are given. That is, we have to find at where the angular position, which angular position there will be stagnation points. Okay. So now what we know is that we know our Cp, that is coefficient of pressure, right? That is 1 minus V by V infinity, the whole square. Okay. So now here what it is given, cylinder placed at a uniform stream of ideal fluid, and axis is normal, with its axis normal to the flow. Okay. So here what is that? So when V is equal to V infinity, Cp is equal to 0. So now we saw in the last class that we know the relation between Cp and angular position. That is Cp is equal to 1 minus 4 sine square theta. Right. So now we know when the flow is normal, so V is equal to V infinity. When that is Cp will be equal to 0, right? So when it is equal to when these both are same, so the Cp becomes 0, right? So now when we substitute 0 equal to 1 minus 4 sine square theta, so sine theta is equal to plus or minus 1 by 2. So we'll get the theta values as sine inverse of plus or minus 1 by 2. That is 30, 150, 210 and 330. That is will be our option A. Okay. So the next question. Okay. Consider a 2D flow with the stream function. That is 2D flow stream function is given. The absolute value of circulation. We have to find the value of circulation along the unit circle center. X is equal to 0, y is equal to 0 is. Okay. So now our stream function is given. That is phi is equal to 1 by 2 ln of root of x square plus y square. What I'm doing is that I'm taking this as single term as r square. R. Okay. Sorry. R. So when I substitute here, I'll get my stream function as psi is equal to 1 by 2 ln r. Okay. So now what I know, we'll be, for next thing, we have to find our velocity. What is our circulation formula? Circulation is capital gamma is equal to minus closed integral of v vector dot ds vector, right? So we have to find our velocity. That is, it will be our velocity along radial component and tangential component. That is Vr and V theta we have to find. So Vr, what we know, Vr is equal to 1 by r dou phi by dou theta. So if when we substitute it here, when we equate it here, we'll get Vr is equal to 0. If we substitute for tangent here, that is minus of dou phi by dou r, we'll get V theta is equal to minus 1 by 2r. Okay. So now when we'll substitute it here, and solve it. That is, I'm converting into polar coordinates because we have it in terms of v theta. Okay. So v theta, when I substitute into polar coordinates, what I'll get is I'll get my terms to 0 to 2 pi v theta r into d theta. Okay. When I'm getting this, when I substitute to polar coordinates. So this we have to note. Okay. So next, when I substitute here, okay. So when I substitute here my v theta term, my r becomes cancels and I've integrated. So 2 will get by 2 pi by 2. So we'll get my answer as my circulation will be pi. That is option D. Okay. So the next one. Next is a very important question. So, okay. Consider a potential flow over a spinning cylinder. Okay. So they have given the stream function. They have given our stream function equation even directly as a whole. Okay. So now, free stream velocity. They have given the value for free stream velocity, circulation, and cylinder radius are the radial and azimuthal velocities. It is nothing but we have to find VR and V theta. Okay. So what we know all the formulas for VR and V theta, right? So we know psi is also given. So psi is equal to V infinity r sine theta 1 minus r square by r square plus gamma by 2 pi ln r by r. That is, it is given in the question even. So next, we have to find the radial velocity, right? So VR is equal to 1 by r dou psi by dou theta. So when we equate it, and at pi by 2. That is at theta is equal to pi by 2, we have to equate because it is also given in the question at the surface where theta is equal to pi by 2. Okay. So when I substitute for theta is equal to pi by 2, I'll get my radial velocity will be equal to 0. Okay. So we have found out one part of the question. So next is we have to find the tangential velocity. It is nothing but minus dou psi by dou r, right? So when I differentiate this with respect to r, we'll get this equation. Okay. So what we know that at the cylinder surface, that is a radial component will be equal to the radius of the cylinder, right? Because we saw this during or non or lifting flow even. Okay. So what r is given? R is given as 1 here. So what will happen? This term becomes 1. So in minus, so circulation is also given. So everything is given. So when we substitute it, we'll get p theta value as minus 75 meter per second. That is our option is option A. That is VR is equal to 0. V theta is equal to minus 75 meter per second. Okay. Okay. So this is like one part of the question. Now next we'll see and next question is also same um with same as data from the above question. Okay. So we have to find the stagnation points. Okay. So what we know for stagnation points, velocity will be equal to 0. So VR equal to 0, V theta is equal to 0. So VR is already equal to 0. So V theta we have to equate it to 0 and we have to find theta. This we have even derived so while we were seeing the lifting flow. Okay. So when we substitute all the values here, we'll get sine inverse of minus 1 by 2. So or theta values will be minus 30 or 120, sorry, 210 or 330. That is 210 or 330. It will be my option A. Okay. So this is how the questions will be based on the elementary flow. Okay. So next question is an interesting question. The potential flow model of a storm is represented by the superposition of sink in a vertex. Okay, how the storm will be? It will be kind of a vertex, right? The stream function can be written as okay. The stream function for that is given. So next, small gamma that is strength that equal to circulation is equal to 100 meter square per second. Assume constant air density is given. We have to find the gauge pressure at the distance of 100 meter from the storm of the eye. That is, if this is the storm's eye, this will be my whole storm, right? So this is called my storm's eye. Okay. So we have to find the gauge pressure at here. So okay, so we have a stream function, right? We have a stream function. We have to find here we have to apply our Bernoulli's equation. Okay, that you have to know because we have to find our pressure here. Okay, so that will be got from Bernoulli's equation. So for that we need our velocities, right? Okay, so first our psi is given and every given thing that is circulation is equal to 100 meters square per second and our R is also given that is 100 meter. Okay. So next is, or we have to find our radial and tangential velocities. That is VR is equal to 1 by R dou psi by dou theta. Okay. So when we equated that, so this will become minus gamma by 2 pi r. Okay. So we know that at r is equal to 0. That is at distance r is equal to 100 meter. So when we substitute here, I'll get my VR is equal to minus 1 by 2 pi meters per second. Okay. Next, we have to find the tangential velocity. Tangential velocity is minus dou psi by dou r equal to minus gamma by 2 pi r. Okay. So we know the circulation. Here, when I substitute, I'll get minus 1 by 2 pi. So here, what is that? The total velocity will be velocity along the radial, that is our magnitude, right? V r square plus V theta square, the whole root. Okay, this will be my total velocity magnitude. We have to know that only to substitute in our Bernoulli's equation. Okay, so when I substitute here, I'll get V is equal to 1 by 2 pi meter square per meter per second. Okay, so we have to, as I told, we have to apply our Bernoulli's equation at the point of interest from at the point far away and taking atmospheric pressure as a reference. Okay. So what we have to find? We have to find pressure. P gauge pressure plus 1 by 2 rho V square. So 1 by rho is given, V square we have calculated it now. Okay, so when we substitute, we'll get our gauge pressure is equal to minus 1.2 divided by 4 pi square. Okay, so this will be by option D, 1.2 divided by 4 pi square. So this is an interesting question. So next is a simple question actually. Direct substitution. Consider flow of an air, that is density is given. Wing is given, span is given. Let free stream velocity, V is also given. That is here they have written it as U. And the average circulation along the wing will be circulation is also given. We have to find lift force acting on the wing. What is it? This is nothing but Kutta-Joukowski theorem, right? That is lift per unit span is equal. What we know from the Kutta-Joukowski, lift per unit span is equal to density, velocity to circulation, right? So it is direct substitution. When you substitute it directly, you will get say 3690. That is, it will be your option C. Direct substitution. Okay. One thing we have to is that we know that lift per unit span is our Kutta theorem, but here they have asked for lift force acting on the wing. So you have to multiply it by your chord length. That is, sorry, you have to multiply it by span here. Okay, that is your extra. You'll multiply it by span, so you'll get for lift force acting on the total wing. This is for the span and this is for total wing. Okay, just remember and note it down. Okay, next. For the maximum value of coefficient, we have the maximum value of coefficient of lift for a 2D provided by at least one stagnation point on the cylinder surface is predicted by the potential flow theory to be. Okay, now we have to find at how much the maximum thing will be. So what we know before even, we know that we have seen on the last lecture even that or there will be for a lifting flow or stagnation point where theta is equal to sine inverse of gamma by 4 pi v infinity r, right? So this term will be always less than 1 because only then we'll have two stagnation point on the cylinder, right? Only that it is valid. So we have to take this, that is the stagnation point depends on this term. Okay. So we can write the circulation as gamma is equal to 4 pi v infinity r. Okay. So that is what it is written here. See, gamma is equal to 4 pi v infinity r. This is how we wrote this equation. Okay. So now what we know from the Kutta-Joukowski theorem, that is lift per unit span is equal to rho infinity v infinity circulation. That is and what we know q infinity, sorry, rho infinity. So equal to 1 by 2, sorry, this is q infinity. So 1 by 2 rho infinity v infinity square s into cl, right? So what we know s is equal to B into C, right? So when we substitute here, we'll get our CL value equal to 4 pi. That is, or this will be our answer. Okay. Okay, that's all our that is all our problems. And now we'll move on to the next. That is airfoil nomenclature. Okay. So airfoil nomenclature will be asked for max minimum will be asked for 1 marks. So few questions will be asked. Okay. So now we'll see from the basics. First, airfoil shapes are defined by National Advisory Committee of Aeronautics. That is nothing but NACA. That is what the full form is. National Advisory Committee for Aeronautics. Okay. So now we'll see our all terms. So first, this is our airfoil, right? So the straight line joining the leading edge and the trailing edge is our chord line. Okay. So the mean camber line is nothing but it is the line drawn at the equidistance from both upper and lower surface of the airfoil. Okay, that is my mean camber line. The minimum distance between, that is the distance between my mean camber line and the chord line is called as the maximum camber. Okay, so this will be my upper camber and this surface will be my lower camber. Okay, so the distance where my airfoil is very thick, that is called as a maximum thickness. That region is called as maximum thickness. And the front part, that is this portion, is called as a nose circle. That defines how circle, that is how blunt the leading edge is. Okay. So these are all the main terms which we have to remember while seeing for the NACA nomenclature. Okay. First is NACA 4-digit. NACA 4-digit is nothing but just with 4 terms. Okay. So first is we'll see what first is for NACA 2422. Okay. So we'll start from naming from uh from left to right. Okay. So first, what is this 2 is that 2 is or 2% of maximum camber. Okay, maximum. What is our maximum camber? That is the distance between the mean camber and the chord line will be my maximum camber. That is 2% of maximum camber. It is NACA nomenclature will be always in terms of percentage of chord. Okay, so that is 2%. Next term is 4. That 4 is we have to multiply it with to 10. So that is 40%. So that is my location of maximum camber. At 40% from the leading edge will be my location of maximum camber. Then the last 2 digits will be my, that is 22% will be my maximum thickness. That is will be my maximum thickness. Okay. So this is my 4 digit. First is maximum camber. Next is location of maximum camber. Next is maximum. The last 2 digit will be always maximum thickness. Okay. So this is for a cambered aerofoil. Now we have the C for symmetrical airfoil. For symmetrical airfoil, the first 2 digits will be always equal to 0 because there is no camber here. So the rest or the remaining 2 digits, that is 11%. That is, it is the maximum thickness, right? So it is 11% maximum thickness. Okay. So this is for NACA 4 digits. Okay, now we'll move on to the NACA 5-digit series. Okay, so now we have taken NACA 23013. Okay, so here also we'll start naming from left to right. So first is 2, right? So 2 in 5-digit series, you have to remember that the first 2 that gives us our design lift coefficient. That is, it is the value for CL where our airfoil performs efficiently. Okay. So here the first digit into 0.15, that is will be 0.3, right? So that is called as design lift coefficient. Okay. So next to 2 digits, that is the middle 2 digits will when we divide by 2, we'll get the location of maximum camber. Okay. So the last 2 digit will be our maximum thickness. Mostly last 2 digits will be our maximum thickness. Okay. This is my NACA 5-digit series. Next is we'll see NACA modified 4 and 5 digit. Okay. So now here we have taken NACA 0004-63. Okay. So here from by seeing even we can see that. See, just understand that this is a 4 digit and this is a separate 2 digit. Like think as of it. Okay. So what we'll see, so this is symmetrical, right? So no camber, that is symmetrical. The last 2 digits from or four digit NACA terms will be my maximum thickness. So maximum thickness is written. After the dash, this is our dash, and the first term after the dash refers to the roundness of the nose. That is how blunt the nose is. Okay, how it refers to roundness of the nose. If it is 6, it is the nose has some roundness. If it is 0, it has a sharp leading edge. Okay. Next term after the roundness of the nose is the location of maximum thickness. Okay, that is for the location of maximum thickness, we'll always multiply it into 10. Okay, that is 30%. Okay. So next is we'll see a series of NACA. We'll see some series of NACA series. Okay. So first is NACA 1 series. Okay. So NACA 16-214. Okay. That is, it is modified of 5 digit, right? So NACA 16-214. So we'll start from left to right even. So first will be our series. Second term will be my location of minimum pressure point. Okay. That is, the location of minimum pressure point is where my CP reaches the lowest value. Okay. So now that will be my 6 into 10. So it will be 60%. That is 60% of the camber. sorry, 60% of chord, sorry. So next, after the dash, the first term after the dash will be my design lift coefficient, as we saw here even, okay. So here it is our design lift coefficient. So there we saw it is our roundness. And then the last two digits will be my maximum thickness, percentage of maximum thickness, okay. Every term, every Naga series will vary slightly, so we have to notice it. Okay, so maximum thickness. This is my NACA 1 series. Now we'll move on to NACA 6 series. NACA 6 series will be used is mostly a laminar airfoil. Okay, so NACA 641. This one is written as subscript. Okay, dash 214. Okay, and A is equal to 0.6. I'll tell you what this A later means. So first, this is we'll move on to left to right even. So first is it is a NACA 6 series, and the next four will be my 4 into 10, that is location of minimum pressure point. Okay. See this in the last term. For the series it is written for the second term will give us the location of minimum pressure point. Okay. And the subscript 1. So into that subscript 1, if you multiply 0.1, you'll get you'll get a value where the low drag is maintained above or below the design lift coefficient. Okay, so if our design lift uh, to our design lift coefficient, it will be 0.1 above or 0.1 below the term where the drag will be maintained. Okay. So next term after the dash will be my design lift coefficient. That will be found by this term into 0.1. Okay. So that will be my design lift coefficient. And the last two will be my maximum thickness. That is same for all the many NACA series. Okay. So 14 percentage of maximum thickness. Now I'll tell what this A is. A equal to 0.6 will be my pressure distribution. That is, which the uniform pressure distribution along the surface. That is, which is uniform up to 0.6 chord or 6 percentage of the chord. If this A value is not given, it is taken as 1. That is, A is taken as 1. Okay. Okay, so next we'll move on to NACA 7 series. Okay, it is the NACA 6 series is for laminar airfoil. Now we'll see for further extension to laminar airfoil. Okay, so we'll have nothing but we'll have an extra term here. Okay, that is we'll have an alphabet here. So now we'll first when we see it even we can say that it is a NACA 7 series. Okay, one thing is found. Next is 4. 4 is nothing but same, right? For the location of minimum pressure point, which is found by multiplying into 10. It is 40 percentage. Next is here, the 7 is on the lower surface. That is, this will be my upper surface and this will be my lower surface. So it's 70 percentage. That is location of minimum pressure point. This is for upper surface. Okay. And this is for lower surface. Okay. Upper surface and this is for lower surface. The next A, the value A, or the alphabet A is nothing but our specific for profile. That is a different kinds of camber, different forms of camber used. This can vary also because for every alphabet there is different types of camber used on the particular airfoil. Okay. So next, the next term, the next digit after our specific profile will be our design lift coefficient that will be found by multiplying into 0.1 and the last two terms will be my maximum thickness. Okay, so this is NACA 7 series. Okay, so next is NACA 8 series. NACA 8 series is for supercritical airfoil. Okay, so first NACA 8 series is given. From the first term even we can find it is the series and next term after is second term is the location of minimum pressure point on the upper surface and the next term to that is location of minimum pressure point on the lower surface. Okay, so the term A will give us the specific profile and same, it is very same to the above thing. Okay. So specific profile, that is type of camber used, and the term and the digit after that will give our design lift coefficient. The last two will give our maximum thickness. So these are all the NACA nomenclature. Okay. So these are all our NACA nomenclature. We'll see. Will be asked for 1 marks. Okay, so next we'll move on to the next theory part. That is some key parameters to be remembered. Okay, we all know that, right? This is just for remembering. That is CL is equal to lift by 1 by 2 rho V square S. And the lift coefficient, drag coefficient, and momentum coefficient. In this, or that will be equal to chord length. Okay, so this is to be remembered for applying problems. Okay, so when we substitute here, it will give for moment coefficient. So it will be by m by 1 by 2 rho v square c square. Okay, that is extra one c will be multiplied here. So these three have to be remembered. The next term to be remembered is aspect ratio. Okay, aspect ratio is nothing but ratio of wingspan to the main chord length, or the square of the span divided by wing area. That is mostly aspect ratio formula will be b square by s. Okay, this will be very important. Okay, there or S. What is S? S is a wing area will be wingspan into chord. Okay. Okay. So now for higher aspect ratio or wing will be long and narrow. Mostly it's used for our commercial airlines. For low aspect ratio, that is or wide or delta wing, all will have or very low aspect ratio. That is, it is mainly used for missiles and fighter jets. Okay. It is for easy maneuverable and short, and it is mostly for short and wide range. Okay, these are all to be remembered. So now next we'll see wing thin airfoil theory. Okay, now we have came to airfoil. So from the name even it is nothing but it is the study for very thin airfoils at a very small angle of attack. Okay, so we'll study how the behavior flow happens and what all and how the lift happens and everything. Okay. So it is fundamental aerodynamic concept that describes the lift characteristics of thin aerofoils at very small angle of attack. It approximates lifting surfaces to zero thickness, that is very minimum thickness, which predicts the flow behavior. Okay. So first we'll move on to the basic assumptions. That is already we saw from the name, it is a very thin airfoil, meaning its thickness has a negligible effects on the flow for very small angle of attack. So the alpha is very small, right? So sine alpha will approximately equal to alpha, and cos alpha will be approximately equal to 1. Okay, so here for airfoil, it is for 2D flow, inviscid and incompressible 2D flow. This have to be known. Of course, airfoil is 2D, right? Okay, so the results of a thin airfoil theory I have directly written here. Mostly it will be for two. One is for symmetrical and another is for cambered. Okay, so first we'll see the CL. Okay, that is lift coefficient. So lift coefficient increases linearly with angle of attack. Okay, that is for a symmetrical airfoil, CL is equal to 2 pi alpha. And for cambered airfoil, that is CL is equal to cambered airfoil, CL will be equal to 2 pi alpha minus alpha when lift is equal to 0. So this is a this hereafter what are all the equations we see, that is all very important to solve problems. Okay. So CL is equal to 2 pi alpha, and for cambered airfoil it will be 2 pi alpha minus alpha when lift is equal to 0. Okay. That is angle of attack when lift is equal to 0 is nothing but alpha L is equal to lift is equal to 0. Okay. For symmetrical aerofoil, alpha at lift is equal to 0 will be equal to 0. For cambered aerofoil, alpha at lift is equal to 0 will be negative. Okay. This can be known. This have to be known. Okay. Next is moment coefficient about the aerodynamic center. First, we'll see what is aerodynamic center. Aerodynamic center is the point where the moment coefficient remains constant. Okay. Moment coefficient remains constant regardless of the angle of attack. Okay. So for symmetrical airfoil, momentum coefficient at aerodynamic center is 0. For cambered aerofoil, momentum coefficient at aerodynamic center is negative. That is, it is nose down moment. Okay. Okay. Next is aerodynamic center is typically located at quarter chord. This we have to know. Typically located at quarter chord point. That is x is equal to c by 4 for a thin airfoil. Okay. So these are all the things which we have to know for thin airfoil theory. Okay. And these are all the final results which we have to know. This is all very important. Okay. This is for airfoil. That is 2D structure. Okay, so next we'll see Kutta condition. Kutta condition is nothing. We already saw Kutta-Joukowski condition, that is lift per unit span is directly proportional to circulation. So now Kutta condition. Kutta condition is nothing but for a smooth airfoil, the flow must leave the trailing edge smoothly. That is, there must be not any disturbances, and the flow must leave smoothly. Okay, with no flow circulation around the sharp trailing, that there should be no circulation and the flow must leave smoothly. Okay, so the velocity along the trailing edge is finite and for inviscid conditions. Okay, so now for symmetrical airfoil, that is, we have to have that is velocity on the upper surface will be equal to velocity along the lower surface, right? For symmetrical aerofoil. So to be finite, we will be equating it to 0. Okay. So for cambered airfoil, velocity along the upper surface, that is V1, will not be equal to lower surface for cambered airfoil, as there is a camber there. So we will be equating it to 0. Okay. So this is simply our Kutta condition. That is, we have to have a smooth airfoil. Sorry, for a smooth airfoil, the flow must leave the trailing edges smoothly without any flow circulation. Okay. So Kutta condition helps explain why the airfoil generate lift. Okay. By selecting solutions that provides finite trailing edge velocities and specific amount of circulations by this is our Kutta condition, right? So sorry, Kutta-Joukowski condition. For a flow with Kutta condition, flow leaves smoothly and stagnation point lies at the trailing edge for smooth flow, ensuring finite and meaningful velocities. Right, we have to have a smooth flow with finite and meaningful velocities. That is why we are equating it to 0 to find the finite velocities. If it is stagnation point is not proper and we will have an unrealistic velocities, that is it will be infinite number of velocities which we don't want. Okay, so this is all for airfoil. 2D is done. So now we'll see for 3D. 3D is nothing but wing. Okay, this is very important. We'll see now. Okay, now we'll see finite wing theory. Okay, so this theory is a generalization of 2D airfoil to 3D. So we have moved from 2D airfoil to 3D. This includes effects of wingtip vortices and resulting phenomena such as downwash and induced lift. We'll see all these terms one by one here. Okay, so Prandtl's lifting line theory. This is what we are going to see now. That gives an analytical approximation to our finite wing theory. Okay, so from this we'll see the lift distribution, downwash, and induced drag. Okay, so this finite wing theory, that is our finite wing theory will be seeing from terms of Prandtl's lifting line theory. It is a combination of elementary flow, Kutta conditions, and Biot-Savart law. Okay. So, so we have already seen that it is a 3D, right? So this is my 3D wing where my lift is acting along my Z direction here. This is I have taken my coordinates like this, and along the X direction, drag is happening. Okay. So this is my wing with span B, and this is my free stream velocity. Okay. When we give a free stream velocity here, what happens at the tip of the wing will have a distortion, that is wing tip vertices will be formed, and that is called as tip vertex. Okay. So now what I'm taking is as I'm taking this tip vertices first. Okay. And I'm connecting these two tip vertices with a vertex and I'm calling it at the bound vertex. Okay. So this bound vertex is nothing but the vertex which connects both my tip vertices. Okay. So here this tip vertex is called as free trailing vertex, right? So it is as it is free trailing, it is called as free trailing vertex. So this is called as horseshoe vertex. See here, this is my bound vertex and this is my free trailing vertex. And this setup is called as horseshoe vertex, which is important. Okay. Important term to be known. where bound vertex will be my boundary vertex, right? And free trail and tip vertices will be my free trailing vertex. Okay. So now what happens is that this will be my vertex 1 and this will be my vertex 2. I'm taking it like this. Okay. So this vertex 1 and vertex 2 induces velocity at the vertical direction. Okay. This induces velocity here where my velocity will be smaller at the center and will be larger at the tip. Okay, so that can be written, that can be known from this diagram even, that is we have an elliptical thing, that is a curved thing where my velocity will be less at the center and greater at the tip. So from this, lift cannot be generated because our velocity is very less at the center and more at the tips. That will lead to lift distortion and lift cannot be generated. So this is for only one horseshoe vertex, right? This hole is my one horseshoe vertex. So what I'm taking is as now I'm taking multiple horseshoe vertex to increase my velocity and my circulation. Okay. So when I consider multiple horseshoe vertex, this is my multiple horseshoe vertex, that is horseshoe vertex of circulation. This I am taking it for a small part, right? So I'm taking as circulation, that is D capital gamma 1, 2, 3, 3. That is I'm taking three horseshoe vertex here with a strength of that is D gamma D circulation 1 plus D circulation 2 plus D circulation 3. Okay, that is three things I have taken. So now what happens is that the bound vertex, now this is my bound vertex, right? The bound vertex will have a strength. They'll have a certain strength, and this strength, the strength of the bound vertex will depend on how much horseshoe vertex we have added. Okay, see here, bound vertex has a strength now, and it is based on how many horseshoe vertexes are overlapping. Okay, so now in the horseshoe vertex or circulation, there will be a certain amount of circulation with certain strength. Okay, so this the line of the bound vertex is where the lifting line. Okay, okay. So this will be my lifting line. Lifting line is nothing but a conceptual line along the span of the wing. This is my span of the wing, right? Represents that varying circulation at different span-wise location. Okay, for a different span-wise circulation varies. Okay, so at the center of the wing, circulation is maximum. Okay, see, I've drawn it as a big circulation. Circulation is maximum. So near the wingtip, circulation is minimum or decreases to zero because because at the center only lift will be generated and there will be very less or no lift generated at the tip of the vertices, right? So circulation will be equal to zero or very less. And from what happens at the tip, vertex forms. Okay, so this is what is, and this line where the circulation varies is called as a lifting line. Okay, so now this variation in the circulation reflects the lift distribution along the wing. Okay, how much the circulation varies will gives us the lift distribution along the wing. This is only the Prandtl's lifting line theory. Okay, that is variation in the circulation reflects the lift distribution along the wing, and that line is called as lifting line. Okay, so now for an elliptical vertex. Okay, this condition is done. So now I'm taking it for infinite number of horseshoe vertices. That is many number of horseshoe vertices. So that is now what happens is that there will get an elliptical vertex. That is, or strength circulation will be and or circulation will be higher at the center, right? So I'm drawing an imaginary curve here, and that depicts elliptical vertex. Okay, we'll get elliptical distribution, which is ideal case. Okay, so at the center will be my maximum circulation. Okay. So now we'll see the next terms and then we'll move on to that again. Okay. So now the trailing vertices formed at the wing tip induce a downward velocity component behind the wing. Right. So see here, that is, this is my wing. This is my trailing vertices, right? So because of my trailing vertices formed at the wingtip, there is a downward velocity acting behind the wing. This is for front of the wing. This is back of the wing, right? That is called as downwash. Okay. It is denoted by W here. Okay. Downwash. Okay. So downwash, this modifies the effective angle of attack, reducing it and changing the lift's orientation. Downwash changes the lift orientation. That is, see here, this is my airfoil. I have taken an airfoil for here. So this will be my downwash. Right? So what happens because of my downwash, my lift vector will vary from here to here. If my lift vector will vary. When my lift vector changes, there is a backward drag component acting. Okay, this is my lift vector and this is my backward drag component acting. That backward drag component will be my induced drag. Okay, that is DI. This is my lift and this is my DI. For an ideal case, that is for an elliptical lift distribution, infinite, we have taken infinite number of vertices to reduce our downwash, because only when we reduce our downwash, our lift vector will be ideal and will be and that leads to reduce or induced drag, because we don't need this reduced unwanted drag, right? So to reduce that, we are taking our elliptical lift distribution. I hope you understand that. Okay, see this tilt in the lift vector, the backward tilt in the lift vector creates a drag component called as an induced drag. That is, dI is equal to L square divided by pi E A R. That is aspect ratio. Okay, so this is our formula for induced drag. So I have already drawn it here, but this is a detailed diagram. Okay, that is, this is my airfoil. I have taken an airfoil here. Lift vector and the backward force is called as my induced drag, and my relative wind. There is an effective angle of attack and induced angle of attack. Okay, so and this will be my total angle of attack. So effective angle of attack will be alpha minus alpha I. So this is to be known. Okay. So again, this is a small recap. High pressure from below the wing spills. Sorry, from below the wing has high pressure, right? So high pressure from below the wing spills into the region above, forming a trailing vortex, which is, that is, it is nothing but it is a direct result of high pressure and low pressure. That is, it will be your low pressure and that leads to the trailing. These wingtip vertices can be main contributors. Of course, wingtip vertices are main contributors in India's drag, right? So to minimize this induced drag, already we saw that. That is why we are using that elliptical lift distribution. That is, which is an ideal case to minimize, to get a minimized induced drag. Okay. So now we'll see all those expressions. Circulation along the span. Now for circulate. Now the expression for circulation along the span. It's expressed as gamma for y, that is along y direction, is equal to gamma naught into root of 1 minus 2 y by b the whole square. Okay, that is, this gamma naught will be maximum circulation at the center. That is, we saw it, the maximum circulation at the center. Okay. So next B is a wingspan. And the downwash is expressed as downwash. The expression for downwash is expressed in terms of circulation. Okay, that is, I already told downwash is expressed in terms of W, right? So W of y is equal to 1 by 4 pi from minus b by 2 to b by 2. That is our wingspan. Minus b by 2 to b by 2 d gamma by y minus y naught minus y into dy. The y naught and y are just nothing but our span wise positions. Okay. So next is our induced drag coefficient expression. That is CDI is equal to CL square divided by pi EAR. Okay. So next is where we have to find our CL, right? Our CL is nothing but A. We'll have a term A here. So that is nothing but this will be mostly used in problem solving. CL is equal to A into alpha minus alpha when lift is equal to 0, where this A is expressed as A naught divided by 1 plus A naught divided by pi AR per radian. Okay, so to convert into, we have to convert into per degree. So to convert into per degree, we have to find, divide it by 57.3, that is to convert into radian. Okay, so now the term, if A naught is not given, please include it. A naught is equal to, A naught is nothing but dCl by d alpha. Okay, that is, uh, suppose for Cl term, when there is some lift, minus Cl term minus Cl when equal to 0 divided by alpha minus alpha when lift is equal to 0. That is, this term will equal to 0. Okay. Please note it down. I haven't included it here. So this is our A naught. Okay. So these three formulas and these four formulas will help majorly in problem solving. Very important. Okay. Okay, so the last two topics. Next is our critical Mach number. Critical Mach number is nothing but Mach number at which the flow reaches the speed of the sound. That is, Mach is equal to 1. That is our critical Mach number. Okay, so critical Mach number depends on the wing shape. Okay, it mainly depends on the wing shape here. That is airfoil thickness and camber. For thin, low drag airfoils will have higher critical Mach number, and for thick and highly cambered airfoils will have low critical Mach number. So this is our expression for critical Mach number. That is, critical Mach number is approximately equal to 1 by root of 1 plus gamma minus 1 by 2 minus Cp divided by gamma m infinity square. Okay. Plus Cp is the coefficient of pressure and m infinity is my free stream Mach number. Okay, so this is my critical Mach number. It's nothing but Mach number at which my flow reaches the speed of the sound. Okay, so next is my drag divergence Mach number. It is nothing but Mach number where the drag on the airfoil rapidly increases due to the formation of shock wave. After the shock wave forms, or Mach number increases. That is called as, or that thing where the drag on the aircraft rapidly increases due to the formation of shock waves is called as a drag divergence Mach number, denoted by m small dd. Okay, always this have to be known. Drag divergence Mach number is always greater than critical Mach number. Okay, that is, it increase in Mach number becomes so steep that it affects the performance. Drag cannot be more higher also, because of course it affects the performance, right? So this is our equation for drag divergence Mach number. That is, mdd is approximately equal to m critical plus k into t by c, where k is my empirical constant, will be around 0.1 to 0.2 depending on airfoil design, and T by C is my thickness to chord ratio. Okay, so this as a whole is my drag divergence Mach number. And finally, we'll have a small relation between drag divergence Mach number and critical Mach number. That is, MDT is approximately equal to M critical plus 0.05 to 0.10. Okay. So these are all the formulas which we have to remember. All the formulas which we saw in today's lecture are very important. Okay. So that's all. We'll continue our problem solving on the next lecture. Okay. Thank you so much.